Life on Earth exists in extreme places: boiling hydrothermal vents, frozen Antarctic lakes, and deep underground rock miles below the surface. But how far from Earth has life actually been found? And where is the absolute edge of the living world? Today, we're exploring the most distant environments in the solar system and beyond where the conditions for life, or traces of it, might still exist. What's the furthest point from Earth that still has life? Light from the farthest edges of the universe began its journey long before Earth was born. It started moving across space before our oceans existed, before our moon was in the sky, before the first grain of sand formed on any beach that would one day exist here. That light was already racing through darkness before the sun ignited into the star that now warms our planet. It was travelling before the Milky Way looked like the galaxy we know today, before its spiral arms fully shaped themselves, before our corner of space became home. Think about that for a moment. Right now, as you watch this, ancient light is still arriving. Photons that began their trip billions of years ago are only now reaching our telescopes. They have crossed distances so huge that normal numbers stop feeling real. They move past newborn stars, through expanding space, across regions empty enough to make even emptiness feel lonely. And after all that time, they finally touch a mirror built by a species that only recently learned how to stand upright. That species is us, and now, for the first time in history, we are using those mirrors to ask one of the biggest questions ever spoken. Is there life out there? But not just life somewhere nearby. Not just life on Mars, or hidden under the ice of a moon around Saturn's, or floating in clouds above some strange world around another star. We are asking something even bigger. What is the furthest place from Earth that still has life? It sounds simple at first. You might think the answer should be easy. Maybe it is a planet in our solar system. Maybe it is some distant world orbiting another star. Maybe it is a galaxy so far away that its light left before Earth existed. But the deeper you go into the question, the stranger it becomes. Because to answer it, we first have to ask what counts as life. Does it need to walk, swim, breathe, grow, and move? Can life be tiny microbes hidden inside rock? Can it survive frozen for ages and still count as alive? If we detect chemicals in a distant atmosphere that usually come from living things, does that count? If light from a far galaxy shows signs that the ingredients for life were already there near the beginning of time, does that count too? And there is another twist. The only place where life is fully confirmed is Earth. That means the most distant life we know for sure might still be on this planet. It might be a microbe deep below the seafloor. It might be a bird flying above mountains. It might be a human astronaut circling Earth in orbit. It might even be bacteria hitching a ride on a spacecraft leaving the solar system. So this question is not just about distance. It is about evidence, how we know what we know, and how little we still know. And now, we are going to travel farther than any human has ever gone. We'll start in places that seem impossible for life, where darkness crushes everything under miles of ocean water, to mountaintops where air is so thin the body struggles to survive, into orbit where living things face vacuum, cold, and radiation. Then we move beyond the planets, the sun, and beyond the nearest stars, into the deep black between galaxies. And there, near the dawn of time, scientists may have found chemical evidence linked to the processes that make life possible farther away than ever before. If that sounds unbelievable, that is because only a few years ago it would have been. For most of human history, the night sky was just lights in the dark. Beautiful, mysterious, unreachable lights. We told stories about them, mapped them, worshipped them, feared them, used them to cross oceans, and used them to mark seasons. But we did not know what they were. Then science changed everything. We learned that stars are suns. We learned that our sun is one among hundreds of billions inside the Milky Way. We learned that the Milky Way is only one galaxy among trillions. We learned that planets are common, not rare. We learned that water exists in many places, we learned that chemistry does not belong only to Earth. And each discovery pushed the question forward. If stars are suns, then maybe other suns have worlds. If other suns have worlds, maybe some are warm. If some are warm, maybe they have oceans. If they have oceans, maybe chemistry begins. If chemistry begins, maybe life follows. And if life follows often enough, then the universe may be filled with living worlds separated by distances almost too large to imagine. But imagination is not enough. Evidence matters. That is why scientists build machines that can see farther and better than human eyes ever could. Giant telescopes on mountains, radio dishes spread across deserts, space observatories above the atmosphere, instruments so sensitive they can measure the faint dimming of a star caused by a planet crossing in front of it, devices that can split light into colours and read the fingerprints of gases from worlds we cannot directly see. We do not travel there with our bodies, we travel there with data, and what we have started to find is changing the story. Planets are everywhere. Some circle stars smaller than the Sun. Some orbit red dwarfs that glow dimly for trillions of years. Some are rocky like Earth. Some may have oceans deeper than any on our planet. Some are locked so that one side always faces their star while the other remains in endless night. Some may rain glass. Some may have skies rich with steam. Some may hold the right mix of water, rock, heat and time. And time is the secret ingredient people often forget. Life on Earth did not appear the moment our planet formed. It took time for the crust to cool, for oceans to settle, for chemistry to organize itself into something that could copy, adapt, and survive. Then life stayed simple for a very long time. Tiny cells ruled Earth for billions of years before animals, forests, or anything with eyes appeared. That means when we look into space, we are not just looking for planets like Earth today. We may be looking for planets like Earth billions of years ago, worlds where life is only microbial, worlds where oceans hide everything below, worlds where biology has begun, but has not yet become visible from far away. This is where our story gets difficult, because if alien life is mostly small, hidden, and quiet, finding it will be hard. A forest reflects light in one way. A city sends radio noise, but microbes under ice do not wave hello. So scientists often search for signs instead of bodies. Oxygen in an atmosphere can be a sign. Methane together with oxygen can be more interesting because those gases react and should not remain together for long unless something keeps replacing them. Seasonal changes in gases could hint at biology. Certain surface colours might suggest plant-like chemistry. Complex organic molecules may point toward active processes. None of these signs are final proof on their own. But together, they become clues. And clues are how most great discoveries begin. Now imagine taking that method to the extreme. Imagine using a telescope so powerful it can study worlds around stars many light years away. Imagine looking even farther, to galaxies whose light began travelling when the universe was young. Imagine discovering that heavy elements needed for planets and chemistry existed much earlier than expected. Imagine learning that stars formed fast, galaxies matured quickly, and the ingredients for life may have arrived near the dawn of cosmic history. That possibility changes the scale of the question completely, because maybe life did not need to wait for the universe to become old. Maybe biology could begin surprisingly early. Maybe somewhere in those ancient galaxies, on worlds circling first-generation stars, enriched by earlier explosions, oceans formed under dark skies long before our sun existed. Maybe life had already started somewhere, while the atoms that would one day become Earth were still drifting through space. And yet, before we race to distant galaxies, we need to face a humbling truth. We still do not fully understand life on our own world. There are living things on Earth in places once believed impossible. Microbes survive inside rock kilometres underground where sunlight never reaches. Creatures live near deep-sea vents where water blasts from the crust heated by Earth itself. Tiny organisms endure freezing deserts in Antarctica. Others survive acid strong enough to burn skin. Some tolerate radiation levels that would destroy most known life. Every time we expand the limits of where life can survive here, we expand the places it might survive elsewhere. That means the search for the furthest life from Earth does not begin in space. It begins at home. It begins in trenches deeper than mountains are tall, dry valleys where almost nothing seems alive, mountaintops where cold winds strip warmth away, caves sealed off for ages, inside salt crystals, beneath glaciers, and under the sea floor. Because if life can survive in all of that, then maybe the universe has many more chances than we once thought. And then there is us. Humans have already carried life beyond Earth. Every astronaut who entered orbit took trillions of microbes along for the ride. Skin bacteria, gut bacteria, invisible companions that travel with every person. The International Space Station is not sterile metal floating in silence. It is a living habitat. Plants have been grown there. Microbes have adapted there. Human bodies have changed there. So if we ask what is the furthest place from Earth that still has life, one answer might be simple. Wherever humans have gone, wherever our machines have carried living cells, wherever a spacecraft still drifts through the dark with microscopic stowaways clinging to surfaces or hidden in cracks. That could place life beyond Pluto already. But most people mean something else when they ask this question. They mean life that began somewhere else, life native to another world, life not imported from Earth. And that answer remains one of the greatest unsolved mysteries in science. Mars may still hide it underground. Europa may have it beneath ice. Enceladus may spray it into space through water plumes. Titan may host chemistry stranger than anything here. Distant exoplanets may breathe through atmospheres we can barely detect. Ancient galaxies may have built the raw materials for it long before Earth formed. Somewhere in that vast range lies the truth. Maybe the nearest life beyond Earth is only a few months away by rocket. Maybe the closest is under the ice of a moon we have already photographed. Maybe the nearest is on a planet around the nearest star. Or maybe life is common, and the universe is filled with it so thoroughly that the furthest living world is almost unimaginably far away. That is what makes this question so powerful. It stretches from the smallest cell to the largest map of existence. It asks not only where life is, but how early it can begin, how tough it can be, how far it can spread, and whether Earth is rare or ordinary. By the end of this journey, we will see why the deepest ocean trench matters as much as the biggest telescope, why a frozen moon may matter as much as a distant planet. We will see why a faint line in a spectrum can shake astronomy, and why scientists are careful not to claim victory too soon. Every time we thought we were near the edge, we found a larger world waiting beyond it. The edge of the sea became another continent. The edge of the atmosphere became orbit. The edge of the solar system became the stars. The edge of the visible universe became ancient light still arriving. Now the next edge is life itself. Not whether it exists here, but how far it reaches. So stick around as I reveal the furthest place from Earth that still has life. What counts as life? Before we can answer the question of what is the furthest place from Earth that still has life, we need to deal with a problem that hides inside the question itself. What is life? You see, most people feel they already know what life means. We are surrounded by it every day, so it seems obvious. We wake up in a world full of movement, sound, growth, hunger, birth, decay, colour, and endless biological activity. Birds cross the sky. Insects crawl across walls. Trees stretch toward light. Grass pushes through concrete. Pets react to voices. And people fill roads and buildings with motion. Because life is everywhere on Earth, we rarely stop to ask what life actually is in a scientific sense. We rely on instinct, and instinct works well enough at home. The problem is that instinct may fail the moment we search another planet, another moon, or another galaxy where life might not resemble anything we already know. Science cannot use the phrase, "you know it when you see it," as a serious definition. If humanity wants to search the universe, then we need something stronger than feeling. We need traits, patterns, and testable standards. Most living things use energy in some way, maintain their internal order, respond to surroundings, preserve information, and participate in reproduction directly or indirectly through systems that continue their line. Living systems also evolve over time, which means they can change across generations and adapt to pressure from the environment. Those features sound useful, yet even they create complications because nature does not always fit clean categories. A mule is alive but cannot reproduce. A seed may appear lifeless for years and then suddenly grow when rain arrives. Some microbes can shut down activity so deeply that they seem dead, only to recover later. Viruses contain genetic instructions and evolve rapidly, yet many scientists debate whether they should count as alive because they depend on host cells to function. Fire spreads, uses fuel, expands, and responds to conditions, but nobody places it beside bacteria or trees. The deeper we look, the more we see that life is not a neat box with sharp edges. It is a zone with blurry borders. That matters because alien life, if it exists, may sit near those borders or outside our expectations entirely. If we define life too narrowly, we may miss something real because it behaves differently from Earth organisms. If we define life too loosely, we may mistake chemistry for biology and announce a discovery that does not exist. This is why scientists are cautious. A wrong claim about life beyond Earth would be one of the biggest mistakes in modern history, so the standards must be high. When most people picture life, they picture animals first because animals are visible, dramatic, and easy to understand. Animals move with purpose, chase prey, escape danger, search for food, and react in ways our brains instantly recognize. If tomorrow a camera under the ice of Europa captured a creature swimming through dark water, almost nobody would need a lecture on whether it counted as life. The evidence would feel immediate. If a rover on Mars filmed something crawling over sand, the world would stop. Animals are the kind of discovery people imagine because movement feels undeniable. Yet animals are not the basic form of life. They are late arrivals even on Earth. For most of our planet's history, there were no animals at all. Earth remained alive for immense stretches of time before fish, insects, dinosaurs, birds, or humans ever appeared. If someone had visited our world during much of its early past, they would not have found forests or herds. They would have found oceans, storms, rock, and microscopic life doing quiet work beyond normal sight. That means if we search the universe expecting animals first, we may be searching for one of the rarer and later stages instead of the most common one. Plants create a similar misunderstanding because they are powerful, obvious, and planet-changing. Forests cover land, algae fill waters, and photosynthetic life transformed Earth's atmosphere over long ages. Plants helped shape the oxygen-rich world that later allowed complex animals to thrive. If scientists one day detect a distant planet whose surface reflects light in a pattern suggesting widespread vegetation, it would be an astonishing moment. Yet plants are also advanced life. They depend on long evolutionary histories and many earlier biological steps. A planet can be alive without having anything like trees, flowers, or grass. Life may remain microbial for billions of years, just as Earth once did. This is why microbes are so important in the real scientific search for life. Microbes are tiny living organisms, often invisible without microscopes, and they dominate Earth in ways most people never notice. They live in soil, clouds, oceans, lakes, hot springs, ice, underground rock, inside larger organisms, and on nearly every surface we touch. They were here long before humans and would likely remain long after us. Microbes matter because they reveal life in its most durable and widespread form. Some survive intense heat, others survive freezing cold, others tolerate acid, salt, dryness, pressure, or radiation that would kill larger organisms quickly. Some use sunlight, while others draw energy from chemicals released by rock and water deep underground where no sunlight reaches. If life exists elsewhere, there is a strong chance it may be microbial rather than animal or plant-like. Mars, if alive today, may host microbes hidden below the surface. Europa may contain microscopic ecosystems in its buried ocean. Enceladus may hold tiny life forms in warm pockets beneath ice. Distant exoplanets may be biologically active without forests, insects, or visible creatures. The universe may be rich with life that does not make dramatic television. Then there is intelligent life, which is the category that carries the greatest emotional force for humans. Intelligent life usually means beings capable of language, planning, tools, technology, and perhaps communication across space. Discovering another civilization would mean more than finding biology. It would mean finding minds, choices, cultures, and perhaps histories as deep as our own or deeper. Yet intelligence may be rare, brief, difficult to detect, or unlike anything we imagine. Human technological civilization has existed for only a tiny moment compared with the age of Earth. If civilizations rise and fall quickly, then even a universe full of living worlds might contain very few civilizations visible at the same time. They may communicate in ways we cannot recognize, or they may choose silence. For that reason, intelligent life remains possible, but it is not the safest category to assume when asking where life is furthest from Earth. Now, we enter forms of life that complicate the question even more, because not everything alive needs to look active. Some microbes create spores, which are extremely tough resting forms able to survive harsh conditions for long periods. In this state, they may endure dryness, cold, radiation, or lack of food, then revive later when conditions improve. If a spore lies frozen under Martian soil for ages and later wakes, was it alive the whole time, or only potentially alive? Most scientists would say the organism remained viable and therefore still belongs within life. It was paused, not erased. This matters because dormant forms could travel farther and survive longer than active organisms. That leads to another serious idea. If microbial spores can survive inside rock blasted from one world to another, then life or pre-life material might spread naturally through space under the right conditions. If spacecraft accidentally carry surviving microbes outward, then Earth life may already exist farther away than most people realize. Tiny organisms do not need windows, oxygen tanks, or warm cabins. They need only enough protection to endure until conditions change. Another category is fossilized ancient life, and this one changes the wording of the question dramatically. Suppose we discover clear fossils of microbes in ancient Martian rock. Those organisms would not be alive now, but Mars would still become a world known to have hosted life. That would transform science even if every cell had died billions of years ago. It would prove that biology happened at least twice if Martian life formed independently. Yet fossils are records of past life, not present life, so whether Mars still has life would remain unresolved. Now the problem becomes even stranger when we involve great cosmic distance, because distance in space is also distance in time. Light does not arrive instantly. It moves fast, but the universe is so vast that even light takes time to cross it. We see the moon as it was a little over a second ago. We see the sun as it was minutes ago. We see nearby stars years ago. We see distant galaxies millions or billions of years ago. That means when we observe faraway places, we never see their present. We see their past. Imagine a planet 1,000 light years away that shows signs of life through a telescope. We would be seeing evidence from 1,000 years ago. The life there may still exist now, or it may be gone. and we would not know yet. If we detect possible biosignatures in a galaxy whose light began travelling billions of years ago, then we are looking into ancient history. The place may be entirely different today. So when someone asks where life still exists, we must ask whether they mean still alive now, in that location's own present, or still visible to us through arriving light from the past. This is not a trick of language. It is one of the deepest realities of astronomy. Now we come to chemical biosignatures, which may become humanity's first accepted evidence of alien life. A biosignature is a sign in chemistry or environmental patterns that may be caused by living processes. On Earth, oxygen in large amounts is strongly tied to biology because living systems continually replenish it. Methane can come from geology or life, but in certain combinations it becomes interesting. Seasonal gas changes may suggest cycles linked to organisms. Certain complex molecules may hint at biological activity. Strange surface reflectance might one day suggest widespread photosynthetic systems. Yet biosignatures are dangerous if handled carelessly because non-living processes can mimic them. Volcanoes release gases. Sunlight breaks molecules apart and builds others. Unknown planetary chemistry can surprise us. A signal that seems biological at first may later receive a natural explanation. This is why scientists demand repeated observations, competing models, and skepticism before making bold claims. The universe has many ways to fool impatient observers. Now let us turn to the second major phrase in the question, which is, still has life. This sounds simple, but it may be even harder than defining life itself. Does it mean alive now at this exact moment? If so, then how can we know the present state of places whose light takes years or billions of years to reach us? Does it mean life existed at the time the light we now receive was emitted? Does evidence alone count, or must we directly observe organisms? If astronauts live on a station in orbit, does that count as life beyond Earth, even though it came from Earth? Every choice changes the answer. This is why the question naturally breaks into different categories, each with its own winner. If we use the strictest scientific standard and require confirmed living organisms with solid direct evidence, then Earth remains the only known inhabited world. No alien cell has been verified beyond doubt. No Martian microbe has been grown in a lab. No European organism has been captured. No exoplanet animal has been filmed. Under this standard, the furthest place from Earth that still has life may simply be the most distant living point on Earth itself, or Earth's own occupied outposts if we allow transported life. That answer may sound boring, but it is honest. Science often sounds less exciting than headlines because honesty demands proof. The second category is the most distant probable life. This includes places where evidence strongly suggests life may exist, even if direct confirmation is missing. A rocky exoplanet in the habitable zone of its star with water vapor, atmospheric imbalance, and repeated biosignature-like readings would become a major contender. If such a world lies dozens, hundreds, or thousands of light years away, then the distance becomes extraordinary. In this category, life may be farther away than anything humans can physically reach for ages. The third category is the most distant, directly observed organisms, which includes life we have carried outward ourselves. Humans on space stations are living organisms beyond Earth. Plants grown in orbit are living organisms beyond Earth. Microbes surviving inside spacecraft are living organisms beyond Earth. If a deep space probe still carries viable Earth microbes in protected corners, then life may already exist at immense distances from Earth by direct physical location. This is not alien life, but it is still life. Once you see these categories, the confusion disappears. Different people give different answers because they are using different standards without realizing it. One person says the answer is Earth because only Earth is confirmed. Another says the answer must be a distant exoplanet because life likely exists elsewhere. Another says life already rides our machines through the outer solar system. Each may be reasonable inside their chosen rules. There is one more important truth hidden inside all of this. Reality and evidence are not the same thing. The universe may contain countless living worlds right now, yet our confirmed list may still contain only one. There may be oceans under ice filled with microbes, atmospheres shaped by biology around distant stars, and ancient ecosystems in galaxies whose light has not reached us yet. But science cannot simply assume what has not been shown. It must separate what may be true from what is known. That gap is where discovery lives. Every new telescope, rover, probe, and laboratory method pushes worlds from speculation into evidence. A moon once thought frozen solid becomes an ocean candidate. A planet once known only as a shadow becomes an atmosphere with measurable gases. A rock once considered ordinary becomes a possible fossil archive. Better tools do not just add data, they rewrite categories. Today's possibility may become tomorrow's probability. Tomorrow's probability may become future certainty. So what is the furthest place from Earth that still has life? Right now, the strict answer is Earth only. The probable answer may lie on distant exoplanets or in places where biosignatures strongly point to biology. The direct location answer may include life humanity has already carried into space. The final answer depends on what kind of truth we are asking for. That may feel messy, but messy is often what real science looks like before the picture becomes clear. The universe rarely gives simple answers to enormous questions. It gives clues, exceptions, uncertainty, and moments that force us to rethink everything. This question is one of those moments because when we ask where life is furthest from Earth, we are also asking how far life can spread, how early it can begin, how well it can hide, how long it can survive, and whether our world is rare or ordinary. Now that we understand the rules, we can finally begin the real search. The furthest life. We know for certain, Earth itself. Before we can confirm life elsewhere, we need to understand how difficult confirmation really is. We also need to understand something even more surprising. Earth may be only one inhabited planet that we know, but it contains environments so extreme that they expand the possible map of life across the universe. Right now, no alien organism has been directly sampled and confirmed. No microscope has shown a cell from Mars. No spacecraft has returned living material from Europa, Enceladus, Titan, or any other moon. No probe has drilled into another planet, collected active organisms, and brought them home. No rover has watched a true alien microbe grow in front of cameras. No mission has returned a container labelled beyond doubt with life that began somewhere other than Earth. People often hear about signs of life, possible fossils, mysterious gas, or promising chemistry, and assume the case is nearly closed. It is not. Science uses levels of confidence, and the gap between interesting clues and confirmed life is enormous. A strange molecule can come from geology. A pattern in rock can be caused by chemistry. A signal can be contaminated. A reading can be misinterpreted. A machine can detect something real but misunderstood. This is why scientists are careful. If one day the world announces confirmed alien life, that claim must survive years of attack from other experts trying to disprove it. It must be tested from every angle. The evidence must remain strong after skepticism, not before it. That is why Earth remains the only confirmed inhabited world. It is not because scientists lack imagination, it is because they respect proof. Yet while Earth is the only world confirmed to hold life, Earth is not a simple example of life. It is not a calm garden planet where organisms only thrive in warm forests and shallow seas. Earth is more shocking than that. Life here pushes into places once believed impossible. It survives under crushing pressure, freezing darkness, toxic chemistry, boiling water, intense radiation, and total isolation. Every time we thought we had found a limit, life stepped beyond it. That changes everything. Because when scientists search for life elsewhere, they no longer ask only where conditions look comfortable for humans. They no longer ask only where conditions look comfortable for humans. They ask where conditions might be survivable for microbes, fungi, or systems stranger than anything large and familiar. Earth's harshest habitats became training grounds for astrobiology. To understand where life may exist beyond Earth, we first travel into places on Earth where life seems least likely. Imagine descending into the deepest ocean on the planet. Sunlight fades quickly in the sea. Blue becomes black. The water grows colder. Pressure rises every second. Fish become rare. Shapes vanish. The surface world disappears above you. If you continue downward far enough, you reach trenches cut into the ocean floor, scars where tectonic plates meet and one sinks beneath another. These trenches are not small dips in the seabed. They are vast wounds in the crust deeper than many mountains are tall. The most famous is the Mariana Trench in the western Pacific Ocean. Its deepest known point reaches nearly 11 kilometers below sea level. If Mount Everest were placed inside it, the summit would still sit underwater. Down there, the pressure is staggering. It is more than 1,000 times the pressure humans feel at sea level. Every square inch experiences a crushing force that would destroy ordinary equipment and kill surface animals instantly. For a long time, people assumed such depths would be nearly lifeless. Cold darkness, scarce food, impossible pressure, and endless isolation seemed too extreme for biology. Yet when we finally sent instruments and deep diving vehicles into that darkness, the trench answered with a surprise. Life was already there. Microbes have been found in trench sediments and deep waters, quietly living where sunlight never reaches. Some feed on sinking organic material from above. Others use chemical pathways suited to the deep environment. Strange animals also exist in deep ocean trenches, adapted to pressure in ways surface biology once considered unlikely. These ecosystems are not rich forests of abundance, but they are alive. Think about what that means. If life can survive in the deepest ocean trench under crushing pressure and permanent darkness, then oceans beneath ice-covered moons no longer seem impossible. Europa and Enceladus suddenly become more plausible. Deep Earth taught us how to imagine life in deep space. Now leave the ocean and travel to Antarctica, where another hidden world waits under ice. From the surface, Antarctica can appear empty, frozen and hostile beyond reason. Winds race across barren expanses. Temperatures plunge low enough to threaten exposed flesh quickly. Ice stretches for vast distances. But beneath this frozen continent lies a secret that would have sounded like fantasy not long ago. There are lakes trapped under the ice. Some of these lakes have been sealed away beneath kilometers of ice for immense periods of time. They are dark, isolated, cold, and under pressure. No sunlight reaches them, no birds land on them. No forests feed them. They exist like hidden rooms under a frozen roof. One of the most famous is Lake Vostok, buried beneath the East Antarctic ice sheet. Scientists became fascinated by the possibility that water trapped so long might host microbial life. Reaching such lakes is difficult because drilling risks contamination. If you are searching for tiny native life, one careless microbe from the surface can ruin the evidence. So access requires extreme caution. Studies of subglacial environments and related systems have revealed microbial life existing beneath ice in places once thought sterile. Organisms can survive on scarce nutrients, mineral chemistry, and slow biological cycles. They do not need sunlight if other energy pathways exist. Again, Earth changes the search. If life survives in dark lakes beneath thick Antarctic ice, then buried oceans under the ice shells of distant moons become much more serious targets. A frozen surface no longer means a dead world. Ice can hide water. Water can hide chemistry. Chemistry can hide life. Now picture another scene entirely. A lake with water so acidic it can damage skin, dissolve materials, and challenge most known organisms. The air smells sharp. Colours may appear vivid because minerals stain the landscape. To human senses, it feels poisonous and wrong. Some lakes and pools on Earth reach acidity levels near substances we associate with industrial danger. Their pH can approach conditions once thought fatal to life. Yet even here, life appears. Certain microbes known as acid-loving organisms thrive in acidic waters. They maintain internal balance against hostile surroundings and use chemical reactions for energy. Some help produce acid conditions through their own metabolism, shaping the very environment they inhabit. They are not merely surviving in acid, they are living as specialists there. This matters for planets and moons with unusual chemistry. If a world has acidic clouds, mineral-rich brines or harsh fluids, that does not automatically remove life from consideration. Earth has already shown that organisms can adapt to chemical extremes. Now move from acid to heat. At the bottom of the ocean, where tectonic forces crack the crust, seawater can seep downward, heat near magma, react with rock, and burst back upward through hydrothermal vents. These vents release hot, mineral-rich fluids into cold, dark seawater. Some vent systems reach temperatures that would seem instantly destructive. The environment is unstable, toxic by surface standards, and without sunlight. When hydrothermal vents were first discovered in the late 20th century, they shocked biology. Around them lived communities of organisms unlike anything expected. Giant tube worms with red plumes clustered near vents. Clams, shrimp, crabs, and many microbes thrived nearby. The base of these ecosystems was not sunlight-driven photosynthesis like most familiar food chains. Instead, certain bacteria used chemicals such as hydrogen sulfide for energy through chemosynthesis. That discovery was revolutionary. For generations, sunlight had seemed central to complex ecosystems, yet here was life flourishing in darkness powered by chemistry from Earth itself. Heat, minerals, and rock water reactions supported living communities independent of sunlight. The implications reached far beyond Earth. If hydrothermal systems exist beneath the oceans of Europa or Enceladus, then those hidden seas may have energy sources capable of supporting life. If ancient Mars had underground hydrothermal zones, life may once have emerged there. Deep rocky planets elsewhere may host subsurface biospheres entirely cut off from their surfaces. Earth's vents force science to widen the map. Now consider radiation, one of the great enemies of biology. High radiation damages cells, breaks DNA, and increases mutation. To many people, radioactive zones seem like places life should avoid. Yet even here, Earth refuses to behave simply. Certain fungi have been studied in radioactive environments, including areas affected by nuclear disaster. Some species appear unusually tolerant of radiation, and research has explored whether dark pigments such as melanin may play roles in protection or interactions with radiation. Popular descriptions sometimes say these fungi feed on radiation. The reality is more complex than a dramatic slogan, but the key point remains powerful. Organisms can persist and adapt in places saturated with conditions harmful to many others. This matters for worlds exposed to intense radiation, such as moons around giant planets where magnetic fields trap energetic particles. Radiation may sterilize surfaces while leaving protected underground zones livable. Once again, Earth teaches nuance instead of simple limits. We can keep going. Life has been found in salt flats where water activity is low and crystals dominate the landscape. Life exists in deserts so dry they resemble Mars-like conditions. Life survives inside rocks where pores trap tiny moisture films. Microbes live kilometers below the surface in deep crustal environments. Some communities grow so slowly that generations may stretch across long spans compared with surface organisms. Every one of these discoveries weakens old assumptions. There was a time when people imagined life needed moderate temperature, fresh water, oxygen-rich air, sunlight, and stable conditions similar to those comfortable for humans. Earth has steadily dismantled that view. Human comfort is not the standard of life. It is only the standard of humans. This shift is one of the most important changes in modern science. When researchers now examine Mars, they ask where liquid water might briefly appear underground, where salts might keep brines from freezing, where rock pores might shield microbes from radiation, and where ancient hydrothermal systems once existed. When they study Europa, they ask about ocean depth, ice shell thickness, tidal heating, and possible seafloor vents. When they study Titan, they ask whether unfamiliar chemistry could support systems unlike Earth biology. When they study exoplanets, they consider not only Earth-like surfaces, but also subsurface oceans, atmospheric layers, algae, and alternative environments. Earth's extreme habitats did not merely add trivia to biology. They transformed the strategy of the search for life. Yet there is another lesson hidden inside these discoveries. Life on Earth is often microbial in extreme places, not grand and visible. If you descend into hostile environments expecting forests or animals, you may miss the truth. Sometimes life is a film on rock, a colony in sediment, a chemical trace in water, a community hidden inside cracks. That means the first alien life we find may also be subtle. It may not roar, swim, or wave. It may require patience, instruments, and careful interpretation. This is why missions designed to search for life are so demanding. They must avoid contamination from Earth microbes. They must detect tiny amounts of material. They must distinguish living signals from dead organic matter and from non-living chemistry. They must survive harsh environments while carrying delicate tools. They must often do all of this robotically, millions or billions of kilometers away. And even then, one result may not be enough. A strange molecule on Mars might need confirmation from another mission. An unusual pattern in ice from Enceladus may need repeated sampling. A possible biosignature in an exoplanet atmosphere may need years of observation. Science moves carefully because the claim is enormous. So for now, Earth remains the only confirmed inhabited world. But Earth is not only in the small sense. Earth is a vast laboratory of possibilities. It contains examples of life under crushing pressure, under deep ice, in acid, in heat, in darkness, in radiation, in salt, in dryness, and deep underground. It shows that life can be stubborn, inventive, and difficult to erase. It suggests that many worlds dismissed in the past deserve another look. Imagine if we knew nothing of trench microbes. Deep alien oceans would seem hopeless. Imagine if we knew nothing of subglacial life. Ice-covered moons would seem dead. Imagine if we knew nothing of vent ecosystems. Sunless oceans would seem impossible. Imagine if we knew nothing of acid-loving microbes. Harsh chemistry would seem final. Imagine if we knew nothing of radiation-tolerant fungi. Irradiated worlds would seem barren. Instead, Earth gave us counterexamples. That is why the most important planet in the search for alien life is still our own. Before we can understand life elsewhere, we must understand life here in full. Furthest living organisms humans have taken from Earth. The universe beyond Earth may still be waiting for confirmed native life. But Earth life has already begun traveling. It has gone into orbit, walked on the Moon, lived inside stations circling the planet, survived on spacecraft surfaces, and possibly drifted into deep space, hidden in cracks and corners of machines never meant to carry biology. We often speak as if life belongs to planets, forests, oceans, and soils. Yet over the last century, life has started doing something new. It has begun riding technology. For billions of years, life on Earth spread through water, wind, roots, wings, swimming bodies, crawling legs, drifting spores, and chance impacts of rock. Then a new method appeared: rockets, engines, pressurized cabins, metal shells crossing vacuum, human engineering became a vehicle for biology. The moment the first living cell left Earth aboard a machine, the map of life changed forever. The International Space Station orbits roughly 400 kilometers above Earth. That distance may sound small beside planets and galaxies, yet it matters enormously because it places living organisms in an environment nature never gave them on Earth. There is no normal up or down. There is vacuum outside. Radiation levels are higher than on the ground. Temperatures beyond the walls swing violently depending on sunlight and shadow. The station races around Earth at tremendous speed, circling the planet many times each day. And yet inside, humans live there continuously for long stretches of time. That alone is extraordinary. For most of history, all human life belonged to the surface. We were tied to land. Sea level pressure, gravity, atmosphere, weather, and day-night cycles shaped by one rotating world. Now humans have spent years in total combined time living off the surface in orbit. They eat, sleep, work, exercise, repair equipment, run experiments, and look down at Earth through windows while sunrise and sunset repeat many times within a single day. When people ask for the furthest living organisms humans have taken from Earth, astronauts are among the clearest answers. Living human beings have repeatedly travelled into orbit and remained there. Every crew member becomes a direct example of life carried beyond its original habitat. Even with careful cleaning and filtration, a spacecraft with people aboard is not sterile. It is biologically active in thousands of invisible ways. Where humans go, microbes go too. This makes the International Space Station even more fascinating. It is not simply a machine with people inside. It is a closed habitat where humans and microbes interact in unusual conditions. Surfaces are monitored, air systems are filtered, water is recycled. Researchers study how microorganisms behave in microgravity and higher radiation. Some microbes become more stubborn in biofilms, which are slimy communities attached to surfaces. Others may change growth patterns. Managing this hidden life is part of daily space operations. Think about how strange that is. 400 kilometers above Earth, moving faster than a bullet, a metal station carries people, plants in experiments, and countless microorganisms that once belonged only to a planet's surface. If a person asks where confirmed life exists beyond Earth, orbit already provides an answer. Many people assume spacecraft are perfectly clean before launch. In reality, keeping a spacecraft biologically clean is extremely difficult. Engineers build probes in controlled clean rooms where dust, particles and microbes are reduced as much as possible. Workers wear protective clothing. Air systems filter contaminants. Surfaces are cleaned. Parts are handled carefully. But clean does not always mean sterile. Microbes are persistent. Some hide in tiny seams, cracks and protected materials. Some form spores that resist harsh treatment. Even on Earth, hospitals and laboratories work hard to control contamination because microbial survival is a constant challenge. A spacecraft assembled through many steps, materials, tools, and human contact creates many chances for tiny hitchhikers. Scientists have found bacteria able to survive in clean room environments once thought too harsh and nutrient poor for much life. That discovery mattered because if microbes can survive there, some may also survive parts of space missions under the right conditions. Now, add launch. A rocket leaves Earth through vibration, acceleration, heat, and intense mechanical stress. Many organisms would die under direct exposure to those forces, but some protected within cracks, layered dust, or internal compartments might endure. Once in space, vacuum, radiation, and temperature swings create new dangers. Again, many organisms would fail, yet biology is diverse, and some forms are far tougher than intuition suggests. This leads us to one of the most famous tiny survivors ever discussed in space science, the tardigrade. Tardigrades are microscopic animals, often called water bears, because of their shape and movement under magnification. They live in moss, soil, freshwater films, and many ordinary environments on Earth. At first glance, they look harmless and almost cartoonish, but they became famous because of their remarkable ability to survive extreme stress. Under harsh conditions, tardigrades can enter a dehydrated resting state in which metabolism drops dramatically. In this condition, they can tolerate freezing, drying, and other extremes far better than many larger organisms. Space experiments exposed tardigrades to vacuum and radiation under certain conditions, and some survived. Their fame spread quickly because they seem to embody an almost unbelievable truth. Even animals, not just microbes, could sometimes endure space-like hardship. Important details matter here. Tardigrades are not magical creatures casually strolling through space. Survival depends on preparation, exposure conditions, shielding, and species differences. But the lesson Reem expected ain't powerful. Life can be tougher than. Every time organisms survive something once considered impossible, the map of possibility expands. Now step back to a moment that changed human history forever: the moon landings. When Apollo astronauts travelled to the moon, they carried life there directly. They themselves were living organisms, of course, but they also carried the invisible biological passengers that accompany all humans. Skin cells, microbes, traces of organic material, and biological systems all crossed the distance from Earth to another world. For the first time, life from Earth stood on another celestial body. The moon itself is hostile. It has no breathable atmosphere, intense temperature swings, sharp dust, and radiation exposure. It is not a place where unprotected Earth life thrives naturally on the surface. Yet through technology, humans brought living systems there temporarily. Footsteps in lunar dust marked more than exploration. They marked biology leaving its cradle. That moment carries deep meaning. For billions of years, Earth life was limited to one world. Then suddenly, members of that biosphere crossed space and touched another body. Even though the stay was brief and dependent on machines, the boundary had been broken. The Apollo missions also raised issues that became increasingly important later: contamination and planetary protection. If humans bring microbes to another world, can those microbes interfere with science? Could future researchers mistake Earth contamination for native life? Could we accidentally damage environments that might host their own biology? These concerns became serious enough that space agencies developed rules and standards. Planetary protection is the effort to prevent harmful biological contamination in both directions. Forward contamination means carrying Earth organisms to other worlds where they might survive, confuse experiments, or disrupt environments. Back contamination means returning material to Earth that could pose biological risk, however unlikely. Even if the risk is small, the consequences could be significant enough to justify caution. This is why spacecraft bound for worlds of biological interest often undergo stricter cleaning procedures. A probe heading toward a dry asteroid may have different requirements than one heading toward Mars or an icy moon with possible liquid water. The more interesting a destination is for life, the more carefully we try to avoid bringing our own. That alone tells you how seriously science takes the issue. If contamination were impossible, there would be no need for rules. But contamination is possible precisely because life is resilient. Now imagine unmanned probes leaving the inner solar system and travelling outward for decades. Some have gone past Jupiter, Saturn, Uranus, Neptune, and beyond Pluto into interstellar space. These spacecraft were not designed as life support systems. They are machines enduring cold, radiation, and immense time. Most exposed biological contamination would likely die, yet likely is not the same as certain. Could some microbes survive in sheltered niches inside materials, behind panels, or within protected dust layers? Could spores remain dormant for very long periods in deep cold? Could some cells remain viable far longer than expected? These are difficult questions because we cannot easily inspect every aging spacecraft millions or billions of kilometers away. The famous Voyager probes launched in the 1970s are now far beyond Pluto. They continue outward carrying instruments and, in a symbolic sense, carrying traces of Earth civilization through records and messages. But physically, they may also have launched with microscopic contamination, despite cleaning efforts typical of their missions and era. Whether any organisms remain viable today is unknown. If even a tiny number survived in protected states, then some of the furthest living Earth origin life may already be beyond the outer planets, riding silent machines through darkness between the stars. That possibility is astonishing. The furthest living thing from Earth might not be a whale, an eagle, or an astronaut. It might be a dormant bacterium hidden in a forgotten seam of metal, travelling further every second. Microbes are small, adaptable, and difficult to eliminate completely. Spacecraft are complex structures with microenvironments. Time in deep cold may preserve some materials better than heat. Radiation damages life, but shielding and location matter. The result is uncertainty, and uncertainty leaves room for possibility. Not all missions are equal. Some probes received stronger sterilization because they targeted worlds where contamination was a concern. Others, especially early missions, had different standards. Planetary protection evolved over time as our understanding improved. The better we understood Mars, icy moons, and microbial resilience, the more seriously we approached cleanliness. This growth in standards reflects a larger shift in space science. Early exploration focused on reaching places. Later exploration increasingly focused on studying them carefully without ruining the evidence. If we one day detect life on Mars, scientists must be able to ask whether it is truly Martian or an Earth hitchhiker introduced by human missions. That is one reason contamination control matters so much. Finding life is not enough. We must know whose life it is. Now let us return to orbit, because the International Space Station offers another major lesson. Life does not merely survive being transported, it can adapt during transport. Human bodies change in microgravity. Muscles weaken without exercise. Bones lose density. Fluids shift. Sleep patterns change. Microbes also respond to new conditions. Some experiments study how bacteria grow, how cells repair damage, and how plants behave in space. This means life taken from Earth is not static cargo. It changes while away from Earth. That matters for future missions to the Moon, Mars, and beyond. If humans travel for years in deep space, they will carry entire ecosystems of microbes with them. Managing health will require managing those invisible companions. Spacecraft of the future may be biological environments as much as mechanical ones. Plants may become essential too. They can help recycle air, support food production, and improve mental well-being for crews far from home. If so, future deep space missions may carry gardens across the void. Imagine ships crossing space with roots growing under artificial light, while bacteria cycle nutrients in carefully managed systems. That would be Earth life spreading not as contamination, but as deliberate design. We are already seeing the first steps of that future. Seeds have been studied in space. Plants have been grown aboard orbiting stations. Closed-loop life support systems are researched. Humanity is learning that long-term travel may depend not on escaping biology, but on bringing it wisely. That creates a striking contrast. For centuries, ships crossed oceans carrying food, animals, crops, pests, and disease. Human expansion on Earth always moved ecosystems, often with serious consequences. Space travel may repeat that lesson unless handled carefully. Every mission beyond Earth carries biological responsibility. Now ask again, what is the furthest living organism humans have taken from Earth? If we mean direct human presence, then astronauts in orbit and on lunar missions are obvious examples. If we mean persistent life away from Earth right now, then crews aboard space stations qualify whenever occupied. If we mean non-human organisms, then microbes and experimental plants have travelled widely. If we mean maximum distance, then dormant contamination on deep space probes may be the leading contender. The answer depends on definition, but one truth stands clear. Life from Earth has already spread farther than many people realise. We often imagine a future where humanity someday becomes a multi-planet species. In one sense, that future has already begun in miniature. We have maintained human life in orbit continuously for long periods. We have brought life to the moon. We have sent biology outward on robotic craft. We have learned that cells, spores, and tiny animals can sometimes endure the harshness of space better than expected. These are early, fragile steps, but they are real. Could there be life on Mars right now? Mars has held human attention for longer than modern science. Long before spacecraft, people looked at its red glow in the night sky and wondered why it seemed different from the other wandering lights above them. It looked fierce, dry, and mysterious, but also strangely familiar because, unlike distant stars, Mars was clearly a world. It had seasons, polar caps, changing surface shades, and a presence that made it feel less like a point of light and more like a place. As telescopes improved, that feeling only grew stronger. Mars was not just another object in the sky. It was the nearest world that seemed to invite comparison with Earth. And that is exactly why the question of life on Mars has never gone away. Among all planets beyond Earth, Mars matters because it appears to be a world that changed dramatically over time. Today it is cold, dry, thin-aired and harsh at the surface, but the landscape tells a different story about its past. Valleys cut across the ground in patterns that resemble river channels. Sediments lie in layers that suggest water once settled and moved repeatedly. Minerals form that usually need water to exist. Delta-like shapes spread where flowing water once entered standing bodies of water. Ancient shore-like features remain debated in some regions, but enough evidence exists to say something powerful with confidence. Mars was once wetter than it is now. It did not always look like the desert world we see today. That single fact changed planetary science forever because water is not a minor detail. On Earth, wherever liquid water is stable, life becomes much easier to imagine. Water dissolves chemicals, moves nutrients, supports reactions, and creates environments where complexity can grow. If Mars once had rivers, lakes, and perhaps long-lasting wet regions, then Mars once had the kind of environment scientists take seriously when asking whether biology could begin or survive. Mars matters because it may once have been a habitable planet in ways that are difficult to dismiss. Imagine standing on early Mars billions of years ago. The sky may still have looked different from Earth's, and the climate remains debated. But there may have been flowing water crossing the land, ice melting seasonally in some places, groundwater rising to the surface, and basins collecting water long enough to shape shorelines and sediments. Volcanic heat may have created warm local zones. Impacts may have melted ice and created temporary lakes. Underground systems may have remained active long after the surface worsened. It would not have been a copy of Earth, but it may have offered many chances for chemistry to become something more. One of the strongest reasons Mars continues to matter is the presence of ancient river systems. Spacecraft orbiting the planet have mapped channels that branch and merge in ways strongly associated with flowing liquid water. Some cut through crater rims, some carve across plains, and some feed larger basins. These are not random scratches. They look like landscapes shaped by moving fluid over time. In some places, the channels suggest repeated flow rather than one single event. That matters because long-term water activity gives more opportunity for habitable conditions than brief flooding alone. Then there are lake beds, and these may be even more exciting than rivers. Rivers move through landscapes, but lakes can collect sediments slowly, layer by layer, preserving chemical history like pages in a book. Fine mud can settle gently in calm water. Minerals can precipitate from solution. Organic compounds may become trapped and protected. On Earth, ancient lake beds can preserve signs of past environments extremely well. If Mars had lakes that lasted long enough, they could have been ideal places for microbial life and ideal places for preserving evidence afterward. This is one reason modern missions target crater basins and delta regions. A crater that once held a lake becomes a natural archive. Material washed in from surrounding land can accumulate there. If life ever existed upstream or within the lake itself, traces might have settled into mud and become buried. That buried record could survive long after the water vanished. Mars became even more compelling when missions detected organic molecules. It is important to explain this carefully because organic in chemistry does not automatically mean living. Organic molecules are carbon-based compounds, and many can form without biology. Meteorites carry organics. Geological processes can produce some organics, yet their presence still matters because carbon chemistry is central to life as we know it. When rovers identified certain organic compounds preserved in Martian rocks, it showed that some building blocks or remnants of complex chemistry existed there and could survive in protected environments. That does not prove life, but it removes one easy excuse for dismissing Mars as chemically barren. The planet contains ingredients that matter. The real question becomes what happened with those ingredients over long spans of time under Martian conditions. Then comes one of the most famous and controversial subjects in Martian science: methane. Methane is a simple gas, but on planets it can become a mystery because it can come from both living and non-living sources. On Earth, much methane is linked to biology, though geology also produces some. If methane appears in Mars's thin atmosphere and changes over time, scientists naturally become interested. Some observations suggested methane spikes or seasonal variation. Other instruments struggled to confirm those same signals consistently. Some measurements disagreed with others, creating years of debate. This controversy matters because methane on Mars, if real and actively replenished, would imply an ongoing source. That source could be geological reactions underground, release from trapped reservoirs, or possibly microbial life in protected environments. But because the data have been difficult and sometimes conflicting, methane remains intriguing rather than decisive. Mars keeps doing this to science. It offers clues strong enough to inspire, but not clear enough to close the case. If life exists on Mars right now, it almost certainly does not thrive openly on the surface. The surface is punishing. The atmosphere is extremely thin. Liquid water is unstable in most conditions. Temperatures can be severe, and radiation reaches the ground more strongly than on Earth because Mars lacks a thick protective atmosphere and a global magnetic shield like ours. Ultraviolet light from the sun also damages exposed organic material. Any life near the surface would face relentless stress. That is why serious modern thinking has moved underground. One possible habitat is underground brines. Brines are salty liquid water mixtures, and salt can lower freezing points, allowing liquid phases in colder conditions than pure water. If pockets of salty water exist below the surface, even temporarily, they could provide sheltered microenvironments where chemistry continues. Salty water is challenging for life, but Earth hosts organisms that tolerate high salinity. Underground brines would also gain some protection from radiation and surface temperature swings. Another possible habitat is deep rock pores. Rock is not always solid in the simple sense people imagine. Cracks, grain boundaries, and porous spaces can hold moisture, gases, and chemical gradients. On Earth, microbial life exists deep underground inside rock systems, drawing energy from chemical reactions rather than sunlight. If Mars has similar subsurface environments with enough water activity and chemical energy, then deep microbial ecosystems cannot be ruled out. They might be sparse, slow-growing and hidden, but still alive. Ice-covered aquifers are another serious possibility. If liquid water reservoirs exist beneath frozen layers, ice above could serve as insulation and radiation shielding. Even if surface temperatures remain harsh, buried water systems might remain more stable. Such habitats would resemble a pattern seen elsewhere in planetary science: dead-looking surfaces hiding active interiors. Mars may be smaller and colder than Earth, but internal heat, salts, pressure and geology can create local exceptions. The challenge is obvious. These places are hard to reach. You cannot settle the Mars life question by looking only at the top layer of dust. You need to access protected environments where delicate chemistry or living cells might still persist. That requires drilling, careful sampling, contamination control, and instruments able to distinguish biology from geology. This is one reason the question remains open despite decades of missions. The Viking missions in the 1970s were the first great attempt to answer it directly. Viking landers carried biology experiments designed to test Martian soil for signs of metabolism or organic activity. At the time, excitement was immense because humanity was finally testing another planet for life. Some Viking results were puzzling. Certain experiments produced reactions that looked interesting, while others failed to detect expected organic compounds. Over time, many scientists favoured non-biological explanations involving reactive soil chemistry. The results became a lesson in how difficult life detection truly is. Viking did not give a clear yes or no that satisfied everyone forever. Instead, it began decades of debate. That legacy shaped everything afterward. Scientists learned that one instrument or one style of test is not enough when dealing with unfamiliar soil and tiny signals. You must understand the environment, chemistry, mineral context, radiation effects, and possible false positives. Mars would not yield its secrets quickly. Much later, the Curiosity rover arrived with a broader scientific mission and stronger tools. Curiosity explored Gale Crater, a location chosen partly because it once hosted ancient lakes and streams. As it climbed layered terrain, it read the geological history of changing environments. Curiosity found evidence that ancient Mars had habitable conditions in at least some places, including water, essential elements, and energy gradients that microbes on Earth could potentially use. It also detected preserved organic molecules in ancient rocks and contributed important methane observations that kept the controversy alive. Curiosity's greatest gift may have been context. It showed Mars was not just randomly wet once. It hosted environments that appeared genuinely suitable for life in the distant past. That is a stronger statement than simply saying water existed. Plenty of worlds may have water briefly. Habitability asks whether conditions were stable and chemically useful enough to matter. Then came Perseverance, sent to Jezero Crater, a site believed to contain an ancient river delta entering a lake. If you wanted to search for preserved biosignatures, this kind of location is compelling. Deltas gather sediments from wide areas and deposit them where fine material can trap chemical clues. Perseverance carries advanced instruments and, crucially, collects selected rock samples for possible future return to Earth. That sample return concept is vital because there are limits to what a rover can do with instruments packed into a mobile robot. Earth laboratories are vastly more powerful, flexible, and precise than any miniaturized system currently driving on Mars. If sealed Martian samples are eventually returned safely, scientists could analyze them for years with methods impossible to carry there directly. Some of the best chance for a breakthrough may lie in that future. ExoMars, led through international efforts with a strong life detection focus, was designed around another key idea: drill deeper than previous rovers. This matters because the upper surface of Mars has been exposed to radiation and harsh chemistry for long periods. Organic signals near the top may degrade, but material buried deeper could remain better preserved. A rover capable of reaching below the damage zone may access cleaner records of ancient habitability or even modern protected chemistry. That drilling strategy reflects how the field has matured. Early missions often asked whether surface soil itself would simply reveal life. Modern missions ask where evidence is most likely to survive and how deep we must go to find it. So why do we still have no confirmation? One major reason is ambiguous chemistry. Mars has reactive compounds in its soil, complex mineral environments, and conditions unfamiliar enough to produce surprising results. A gas release, molecule detection, or chemical reaction may look exciting until a non-biological explanation emerges. Science must separate signals produced by life from signals produced by geology, radiation-driven chemistry, or instrument interactions. That is hard even on Earth in some cases. On Mars, it is much harder. Another reason is contamination risk. If you are searching for tiny life, bringing Earth microbes or organic traces along can damage the investigation. Space agencies use careful cleaning and planetary protection measures, but zero risk is difficult. Researchers must constantly ask whether a detected signal came from Mars or from us. This caution slows conclusions, but it is necessary. A false claim caused by contamination would be disastrous for credibility. A third reason is access. The most promising habitats may lie underground, within sealed fractures, under ice-rich layers, or inside rocks not yet sampled. We have explored Mars impressively, but only a tiny fraction of its surface and an even tinier fraction of its subsurface. In planetary terms, we have barely scratched the skin of a world the size of a planet. There is also the possibility that Mars hosted life long ago, but does not host it now. In that case, living cells may be gone while fossils or chemical traces remain. Detecting ancient life can be easier in some ways and harder in others. Easier because you can search preserved rocks, harder because geology can mimic biological patterns. The line between ancient biosignature and unusual chemistry can be frustratingly thin. Another possibility is that life exists now but is extremely sparse. Imagine small microbial communities deep underground, metabolizing slowly, isolated in pockets of water, producing faint signals that rarely reach the surface. Such life could evade detection for a long time. Earth has deep biospheres that many people never think about. Mars may as well, if it ever developed the right start. Mars also matters because it may answer a larger question than whether one planet has microbes. If life arose independently on Mars and Earth both, then biology may emerge readily when conditions allow. That would suggest the universe could be full of life. But if Mars had water, chemistry, and time, yet never developed life, then maybe life is rarer and harder to start than many hope. Mars is not just a neighbour, it is a test case. This is why each mission carries emotional weight far beyond its hardware. A rover wheel track on Martian soil is also a human question mark pressed into another world. Every drilled core, every atmospheric reading, every layered outcrop examined by camera asks the same thing in 1,000 different ways. Did life ever happen here? And could it still be happening now? If the answer becomes yes, history changes instantly. Mars would become the first confirmed non-Earth inhabited world. It would also become, by direct verification, the furthest place from Earth known to host native life. That title may one day pass to more distant discoveries, but Mars would hold it first in a way no atmosphere reading from a distant planet could replace. It would be nearby enough to visit with robots, study repeatedly, and perhaps one day examine with human explorers. Biology would no longer be a one-planet phenomenon. Comparative biology between worlds would begin. Did Martian life use DNA or something different? Did it share ancestry with Earth through ancient rock exchange, or did it begin separately? How did it adapt to cold, dryness, and radiation? What chemistry powers it now? Could ecosystems survive underground for billions of years? the ocean worlds, better candidates than Mars. When most people think about life beyond Earth, their minds go straight to Mars. That makes sense because Mars is close, visible, and familiar in ways the outer solar system is not. It has mountains, valleys, dust storms, polar ice, and a surface that feels like a planet humans can imagine walking on. For generations, Mars became the symbol of alien possibility. But as science advanced, something unexpected happened. The strongest excitement in the search for life slowly began shifting away from the dry red deserts of Mars and toward colder, stranger, darker worlds much farther out. These worlds do not look inviting at first glance. They are frozen moons orbiting giant planets, wrapped in ice, battered by radiation, or covered in thick haze. Some receive weak sunlight so far from the sun that noon they would feel dim compared with daylight on Earth. One has lakes not of water but of liquid methane and ethane. Another appears to hide an ocean beneath a shell of ice thicker than mountains. Another sprays water into space through giant cracks like a cosmic fountain. Yet many scientists now see these places as better candidates for life than Mars. That statement would have sounded strange decades ago. How could frozen moons in the deep cold of the outer solar system be better homes for life than a nearby planet that once had rivers and lakes? The answer lies in one simple idea. Surface appearance can mislead. A world that looks dead on the outside may be active underneath, while a world that once looked promising may have lost the conditions life needs long ago. The great shift began when we learned to think below the surface. On Earth, some of the most resilient life exists underground, under oceans, beneath ice, or near chemical energy sources far from sunlight. That lesson changed planetary science. If life does not need open blue skies and warm beaches, then many hidden environments suddenly become possible homes. Instead of searching only for worlds with comfortable surfaces, scientists began asking where liquid water, chemistry, and energy might exist in protected interiors. That question brought three names to the front of the conversation: Europa, Enceladus, Titan. Each is wildly different. Each is extreme. Each challenges old ideas about habitability, and each may hold environments where biology could exist right now. Europa is one of the most fascinating moons in the solar system. It orbits Jupiter, the largest planet around the Sun, in a realm of intense radiation and giant gravitational forces. From a distance, Europa appears bright, smooth, and streaked with long, dark lines crossing its icy shell. It looks like a frozen world, silent and sealed. But beneath that shell may lie one of the greatest prizes in planetary science: a global ocean, not a lake, not scattered pools. Potentially an ocean that wraps around the entire moon beneath the ice. That possibility changed everything when evidence began to build. Measurements of Europa's surface, gravity, magnetic interactions, and geology all pointed toward a hidden salty ocean below the crust. Scientists now widely consider an internal ocean highly likely, though details of depth and ice thickness remain active subjects of study. Imagine what that means. A moon smaller than Earth may contain more liquid water than all of Earth's surface oceans combined. It may be locked beneath ice, hidden from direct view, but the volume could be enormous. If life needs water, Europa immediately became one of the most interesting places in the solar system. But water alone is not enough. A bucket of sterile water in deep cold is not automatically a cradle for life. Biology also needs useful chemistry and a source of energy. This is where Europa becomes even more exciting. Europa is squeezed and stretched by Jupiter's gravity as it orbits. Because the orbit is not perfectly simple, gravitational forces vary over time. That repeated flexing creates internal friction, and friction creates heat. This process is called tidal heating. It is one of the most important concepts in outer solar system habitability, because it means a world far from the Sun can stay internally active. Without tidal heating, Europa might be frozen solid all the way through. With it, the Moon can maintain liquid water below the shell and possibly geological activity at depth. Now imagine the sea floor of Europa, if there is one in contact with rock. Heat from the interior, water moving through minerals, and chemical reactions between rock and ocean could create environments similar in some ways to hydrothermal systems on Earth. On our planet, hydrothermal vent regions host rich microbial ecosystems powered by chemistry rather than sunlight. If Europa has anything like that, then it may possess one of the most compelling habitats beyond Earth. No sunlight would be needed beneath kilometers of ice. Energy from the Moon itself could be enough. That possibility has electrified science for years because it creates a complete package that researchers care about. Liquid water, chemistry, and energy in one place. Not proven life, but credible conditions. Yet Europa is difficult. Its surface is bombarded by radiation from Jupiter's powerful environment. The ice shell may be thick. Reaching the ocean directly would be a huge engineering challenge, but even without drilling through the shell, scientists can learn a great deal through flybys, radar mapping, surface chemistry, and study of possible material exchanged from below. Europa matters because it may be alive beneath a face that looks frozen. Then there is Enceladus, a moon of Saturn that was once considered minor and unremarkable. It is much smaller than Europa and far smaller than Earth. For years, it was not the star of public imagination. Then spacecraft observations transformed it into one of the greatest surprises in planetary exploration. Enceladus erupts. Near its south polar region, giant fractures in the ice release plumes of water vapor, ice particles, and other material into space. Imagine standing near a frozen plain and watching hidden ocean spray burst upward through cracks into the darkness above. That is what Enceladus appears to do. This discovery was extraordinary for one reason above all others. It gave scientists access, instead of drilling through thick ice to reach a buried ocean. Nature was throwing ocean material into space, where spacecraft could sample it by flying through the plumes. Few gifts in planetary science could be more valuable. The plumes indicated an active internal water system connected in some way to the surface fractures. Analysis of plume material found water-rich particles, salts, organic compounds, and signs that the internal ocean interacts with rock below. These are not tiny details. They are exactly the kind of clues astrobiologists hope for when evaluating habitability. Organic molecules in this context do not mean life has been found. Organic chemistry can arise without biology, but organics are relevant because carbon compounds are central to life as we know it. Their presence in ocean-derived plume material strengthens the case that Enceladus contains useful chemistry. Then came another important clue: silica grains. Certain silica particles detected in plume material have been interpreted as consistent with hot water reactions between liquid water and rock at the seafloor or interior. In simpler terms, scientists saw evidence suggesting water may be interacting with warm rock below, potentially in hydrothermal-like conditions. That is a major deal. Where warm water meets rock, chemical gradients can form. Minerals dissolve and reform. Energy becomes available to microbes on Earth in similar settings. If Enceladus has long-lasting water-rock interactions powered by internal heat, then it may host one of the most promising environments for microbial life in the solar system. And unlike Europa, Enceladus offers samples through natural plumes. That means a future mission could fly through those plumes with advanced instruments designed specifically to search for complex organics, unusual isotopic patterns, cell-like particles, or other biosignatures. In theory, one of the easiest ways to search for alien ocean life in the solar system may be to fly through a moon's spray. Now we move to Titan, Saturn's largest moon, and one of the strangest worlds ever discovered. Titan does not immediately scream life in the familiar sense. It is cold, wrapped in a thick atmosphere, and famous for lakes and seas not of water, but of liquid methane and ethane on the surface. Rivers, rain, shorelines, clouds and weather cycles exist there, but built from hydrocarbons instead of water in the surface environment. That alone makes Titan extraordinary. It is the only moon in the solar system with a dense atmosphere and stable liquids on the surface. Its landscapes include dunes, channels and large northern seas. If you stood there with proper protection, you would witness weather on a moon far from the sun, under an orange sky thick with haze. At first, Titan seems less suitable for life because surface temperatures are extremely cold, and liquid water is not stable on the open ground. But Titan excites scientists for two different reasons. First, many models suggest Titan may also possess a subsurface water ocean beneath its icy crust, adding another hidden water candidate to the list. Second, Titan offers something else almost nowhere else does: rich exotic chemistry happening openly at the surface and in the atmosphere. Sunlight and energetic particles drive reactions in the upper atmosphere, producing complex organic compounds that drift downward. Hydrocarbon lakes, atmospheric chemistry, and long-term environmental cycles create a natural laboratory for chemical complexity unlike anything on Earth. Some scientists ask whether forms of life very different from Earth's could theoretically use such environments, perhaps relying on solvents other than water or chemistries unfamiliar to biology here. This remains speculative, but scientifically interesting. Even if Titan's surface never hosts life, it may reveal steps of chemistry relevant to how life begins. Titan broadens the imagination of astrobiology. It reminds us that not every living possibility must look like Earth. So why do these ocean worlds and strange moons excite scientists so deeply, sometimes even more than Mars? The answer can be reduced to three essentials: liquid water, chemistry, energy. These are not magical words, but they are practical ones. Water allows molecules to move, meet, react, and organize. Chemistry provides building blocks and usable reactions. Energy powers metabolism or pre-biological systems. Where all three persist over long periods, habitability becomes a serious conversation. Mars certainly had some of these ingredients in the past, and perhaps hidden versions of them now. But many Martian surface environments appear harsh and dry today. In contrast, Europa and Enceladus may contain present-day oceans. Not ancient lakes that vanished billions of years ago, but active water systems now. That immediacy matters. Scientists are not only asking what happened there once, they are asking what may be happening there right now. That shift from ancient habitability to current habitability is powerful. If life on Mars existed long ago, we may need to search for fossils or faint remnants. If life exists in an ocean world today, living ecosystems may still function. That creates a very different scientific target. There is another reason these moons excite researchers. Hidden oceans may be protected environments. Surface radiation, impacts, and extreme weather can destroy or degrade delicate biosignatures. But beneath ice, an ocean may remain stable for immense timescales. Ice can shield radiation. Water can circulate nutrients. Tidal heating can continue for ages. A subsurface sea may offer continuity that exposed surfaces cannot. On Earth, some of the most ancient and stable habitats are not always the obvious ones. The same may be true elsewhere. Now imagine the moment of discovery. Suppose a future mission flies through the plumes of Enceladus and detects unmistakable cellular structures, repeating complex molecules with clear biological patterns, or direct evidence of metabolism. Suppose Europa missions identify material from below containing signs no geology can explain. Suppose Titan surprises everyone with chemistry crossing into clear biology. What would happen? Those worlds would instantly become the first directly confirmed native life beyond Earth in our solar system. In distance terms, they would also become the furthest directly confirmed native life known to humanity at that moment. Mars would remain important, But these moons would claim a more dramatic title because they are farther away and biologically distinct environments. The meaning would be enormous. Life would no longer be tied to one planet type. We would know that biology can emerge or survive in buried oceans under ice, in places warmed not by sunlight, but by gravity and internal energy. The classic picture of a habitable zone around stars would need expansion. Worlds far from the Sun, once dismissed as frozen dead zones, would become living candidates. It would also raise immediate questions. Did life on those moons begin independently, or was material exchange long ago through impacts across the solar system? How common is microbial life in ocean worlds? Are there ecosystems layered by depth, chemistry, and temperature? How fast do they evolve in dark oceans? What biochemistry do they use? Are they sparse films on rock, drifting cells in water, or rich vent communities unlike anything on Earth? These questions would define generations of research. Even before discovery, these moons already teach us something important. Habitability is more creative than early science imagined. The Sun is not the only heat source that matters. Surfaces are not the only habitats that matter. Oceans need not lie under open sky. A world can look frozen and still be active inside. That lesson changes how we search the galaxy. If moons around giant planets here can host hidden oceans, then moons around exoplanets may as well. If tidal heating works here, it likely works elsewhere. If chemistry thrives in dark water under ice, then habitable environments may be far more common than just Earth-like planets with blue skies. This means Europa, Enceladus, and Titan are not only local targets, they are prototypes for countless unseen worlds beyond our solar system. There is also a poetic irony in this story. For centuries, humans looked for life under the light of the sun, on surfaces we could imagine walking across. But some of the best places may be in darkness beneath ice, where no sunrise has ever been seen. We expected deserts and continents. Nature may prefer hidden seas. That does not mean life certainly exists there. Beyond the solar system. Beyond the solar system, the search for life moves into a completely different scale, one that is no longer about walking through landscapes, drilling ice or sampling plumes from nearby moons, but instead about reading faint signals carried across unimaginable distances of space, because every confirmed exoplanet we know exists not as a visible world we can study directly, but as a distant shadow of light changes, gravitational effects, or spectral fingerprints hidden inside starlight. And this shift alone changes everything about how we think of life beyond Earth, since we are no longer looking at surfaces or oceans directly, but instead trying to interpret clues carried by photons that have travelled for years, decades, or even centuries before reaching our instruments. Meaning that when we talk about exoplanets with potential for life, we are talking about worlds we cannot see in detail at all, but only infer through extremely careful measurements of light, motion, and chemistry. Over the last few decades, thousands of these planets have been discovered around other stars, and this number continues to grow as telescopes become more sensitive and survey larger portions of the sky, revealing that planets are not rare exceptions, but common features of the galaxy, orbiting nearly every type of star we observe, from small red dwarfs to stars similar to our Sun. And among these countless worlds, a small fraction fall into a region called the habitable zone, which is not a guarantee of life, but a simple physical idea describing where temperatures might allow liquid water to exist on a planetary surface if the atmosphere is suitable, meaning the planet is not too hot for water to evaporate completely and not too cold for water to freeze entirely, creating a narrow band of orbital distance where Earth-like conditions could theoretically exist under the right atmospheric pressure and composition. This concept is extremely important because it provides the first filtering system in the search for life beyond our solar system, allowing scientists to narrow down thousands of planets into a smaller group that might be worth closer study. Even though being in the habitable zone does not guarantee oceans, atmosphere stability, or biological activity, since planetary conditions depend on many additional factors such as magnetic fields, atmospheric retention, geological activity, and long-term climate stability, all of which determine whether a world remains suitable for life or becomes hostile despite its position relative to its star. Among the most discussed exoplanets in this category is Proxima Centauri b, a planet orbiting the closest star system to our own Sun, located just over 4 light-years away, which in cosmic terms is extremely close, but still far beyond any current human travel capability, and this planet orbits within the habitable zone of a red dwarf star, meaning it receives enough heat that liquid water could theoretically exist on its surface, although the conditions are complicated by the fact that red dwarf stars can produce strong stellar flares and radiation bursts that may strip atmospheres or alter surface conditions over time, making the long-term stability of any potential life environment uncertain. Even so, Proxima Centauri b remains one of the strongest early candidates for studying potentially habitable exoplanets because of its proximity, allowing future telescopes to examine it in greater detail than more distant systems, possibly detecting atmospheric composition or seasonal variations if technology continues to improve. Another major system that has captured scientific attention is TRAPPIST-1, a compact system containing multiple Earth-sized planets orbiting a single ultra-cool dwarf star, several of which lie within or near the habitable zone, creating one of the most promising multi-planet environments for comparative planetary science beyond our solar system, since having several similar-sized planets in one system allows researchers to study how different orbital positions affect temperature, atmosphere, and potential habitability under the same stellar conditions. And this system is especially interesting because at least some of its planets may retain atmospheres and possibly even liquid water, depending on their composition and internal heating processes. In addition to these nearby and compact systems, there are also larger and more distant exoplanets, such as Kepler 442b, which orbits a star similar to our Sun at a distance placing it within the habitable zone. And this planet is often considered one of the more Earth-like candidates discovered so far because of its estimated size and temperature range, although like all exoplanets, it remains beyond direct imaging at the level needed to confirm surface conditions or biological activity, meaning that everything we know about it comes from indirect observation and modelling rather than direct exploration. There are also many TOI planets discovered by the Transiting Exoplanet Survey satellite, which continue to expand the catalogue of potentially habitable worlds by detecting dips in starlight caused when a planet passes in front of its star, allowing scientists to estimate size, orbital period, and sometimes atmospheric features when combined with follow-up observations. These discoveries collectively show that Earth-like planets may be far more common in the galaxy than once believed, but they also highlight how limited our current observational tools still are when it comes to determining whether these planets actually support life. The main methods used to study exoplanets are indirect, relying on subtle changes in starlight rather than direct imaging of planetary surfaces, with the transit method being one of the most important techniques, where astronomers observe a small and periodic dimming of a star's brightness caused by a planet crossing in front of it, which allows calculation of the planet's size and orbital period. And when combined with spectroscopy during transit, it becomes possible to analyze how the planet's atmosphere filters starlight, revealing chemical signatures of gases that absorb specific wavelengths. Another key method is the wobble method, also known as radial velocity detection, which measures tiny shifts in a star's motion caused by the gravitational pull of an orbiting planet, allowing scientists to estimate the planet's mass and confirm its existence even when it cannot be seen directly. And when both transit and wobble methods are combined, they provide a more complete picture of a planet's density and possible composition, distinguishing between rocky Earth-like worlds and gas-dominated planets. Spectroscopy plays a central role in this entire process because it allows scientists to break starlight into its component wavelengths and identify chemical fingerprints within a planet's atmosphere when the light passes through or reflects off it, revealing the presence of molecules such as oxygen, carbon dioxide, methane, and water vapor under the right conditions. And these chemical signatures are extremely important because they may hint at planetary processes that are difficult to explain through geology alone if found in certain combinations or imbalances. When scientists talk about potential biosignatures on exoplanets, they focus on a few key indicators that could suggest biological activity, although none of them alone is definitive proof, starting with oxygen, which on Earth is heavily influenced by life through photosynthesis, meaning that large amounts of oxygen in a planet's atmosphere could indicate biological replenishment if other chemical conditions do not explain its presence, although oxygen can also be produced through non-biological processes, such as water vapor breakdown under ultraviolet light, which is why it cannot be treated as a standalone confirmation of life. Another important biosignature candidate is methane, especially when found in combination with oxygen or other reactive gases in a state of imbalance, because methane tends to break down relatively quickly in planetary atmospheres, meaning that if it is detected in significant quantities alongside oxygen, it may suggest a continuous replenishing source that could be biological or geological. And scientists pay close attention to these chemical disequilibria because they may indicate active processes rather than static atmospheric conditions. Water vapor is another key focus because it directly suggests the presence of liquid water somewhere on the planet's surface or atmosphere. And while water vapor alone does not indicate life, it strengthens the case for habitability when combined with suitable temperatures and atmospheric pressure, since water is a fundamental solvent for known biological chemistry. Scientists also look for seasonal changes in atmospheric composition or surface reflectivity, which could suggest dynamic processes occurring on a planet over time, although interpreting such changes is extremely difficult from light years away and requires repeated long-term observations with highly sensitive instruments. Despite all these tools and methods, the major challenge in studying exoplanets remains the same. We do not see forests, oceans, or animals on these worlds, and we do not receive images of their surfaces in detail. Instead, we only receive faint traces of light that have been altered by distance, motion, and atmospheric filtering, meaning that every conclusion we draw is built from extremely limited data points that must be carefully interpreted to avoid false assumptions, and this is why even the most promising exoplanets remain candidates rather than confirmed habitats. The launch of James Webb Telescope. The launch of the James Webb Space Telescope marked a turning point in the way humanity studies planets beyond the solar system, because for the first time we gained a tool capable of looking at distant worlds, not just as points of light blocking or wobbling stars, but as atmospheric systems with chemical fingerprints that can be measured in detail. And this shift is important because it moves exoplanet science away from simple detection into the early stages of atmospheric analysis, where scientists can begin to ask not only whether a planet exists or where it orbits, but what its air is made of and whether that air contains combinations of gases that might hint at active processes on its surface or within its environment. The key strength of this telescope lies in its ability to observe infrared light, which is a type of light that is invisible to the human eye, but extremely useful in astronomy, because many molecules in planetary atmospheres absorb and emit infrared radiation in unique patterns, meaning that by studying how starlight changes as it passes through a planet's atmosphere, scientists can identify gases such as water vapor, carbon dioxide, methane, and other chemical components even across enormous distances. And this capability allows researchers to begin building atmospheric profiles of exoplanets in a way that was not possible with earlier instruments that were more limited to optical wavelengths. Another important advantage of this telescope is its ability to see through dust and gas that would normally block visible light. because infrared radiation can pass through regions of space that appear opaque in other wavelengths, allowing scientists to observe star-forming regions, distant galaxies, and planetary systems that were previously hidden behind thick clouds of cosmic material. And this is particularly important for exoplanet research, because many planetary systems form in dusty environments where early observations were difficult or impossible, meaning that the telescope not only improves our ability to study known planets, but also expands the number of systems that can be examined in detail. By combining this ability with high-sensitivity instruments designed to detect extremely faint signals, the telescope can measure tiny changes in starlight caused by planets passing in front of their stars, and it can break that light into detailed spectra that reveal atmospheric composition, temperature clues, and possible chemical interactions occurring in those distant environments. One of the most discussed targets observed by this telescope is K2-18b, a planet that has attracted significant attention because it lies within the habitable zone of its star and appears to have a relatively low density compared with purely rocky planets, suggesting it may have a thick atmosphere or even a water-rich environment beneath its gaseous layers. And when the telescope analysed its atmosphere, it detected the presence of water vapour, along with other carbon-based molecules, which immediately made it one of the most interesting candidates for further study in the search for potentially habitable environments beyond Earth. What made K2-18b especially controversial was the later discussion of a possible detection of a molecule called dimethyl sulfide, which on Earth is primarily associated with biological activity, particularly from marine microorganisms. And this sparked intense interest because if such a molecule were confirmed in significant quantities on another planet, it could suggest the presence of active biological processes, although this interpretation remains highly debated and far from confirmed. The reason for the debate is not because scientists are ignoring the possibility of life, but because the process of identifying molecules at such distances is extremely complex and requires careful separation of signal from noise, instrument effects, and overlapping spectral features. And even when a signal appears to match a specific molecule, it must be tested repeatedly under different conditions and observational methods to ensure that it is not caused by data processing errors or alternative chemical explanations that could produce similar spectral signatures. In the case of K2-18b, the data has been interpreted by some researchers as suggestive of dimethyl sulfide, but other scientists caution that the signal is not strong enough to rule out non-biological explanations, and therefore additional observations are required before any strong conclusion can be made. This cautious approach is central to how modern exoplanet science operates, especially in the James Webb era, because while the telescope provides unprecedented detail compared with earlier instruments, it still operates at the limit of what is physically possible when observing planets light years away, meaning that every detection must be treated carefully and verified through multiple independent observations before it can be considered reliable. This is particularly important when dealing with potential biosignatures, because the history of science has shown that many initial claims of extraordinary findings can later be revised or reinterpreted as new data becomes available. And researchers are aware that the discovery of life beyond Earth would be one of the most significant scientific events in human history, requiring an extremely high level of confidence before acceptance. Another major area of focus for the James Webb Space Telescope is the TRAPPIST-1 system, which contains several Earth-sized planets that pass in front of their star regularly, allowing repeated observations of their atmospheres over time. And while the telescope has not yet confirmed detailed atmospheric compositions for all of these planets, it has provided important constraints on their possible conditions, helping scientists narrow down which worlds may retain atmospheres and which may have lost them due to stellar radiation or other environmental factors. This system is particularly valuable because it allows comparative study between multiple similar planets under the same stellar influence, giving scientists a rare opportunity to examine how small differences in orbital distance can lead to very different planetary outcomes. In addition to individual planetary systems, the James Webb Space Telescope has also been used to observe some of the earliest galaxies in the universe, revealing structures and light from periods much closer to the beginning of cosmic history than previously possible. And while this does not directly relate to exoplanet life detection, it provides important context for understanding how quickly chemical elements necessary for planets and potentially life formed after the Big Bang. By studying these early galaxies, scientists can trace how elements like carbon, oxygen, and nitrogen spread through the universe, eventually becoming the building blocks of planets and biological chemistry, which connects large-scale cosmic evolution to the smaller-scale question of habitability on individual worlds. What makes the current era especially significant is that for the first time, scientists are not only discovering exoplanets in large numbers, but also beginning to analyze their atmospheres in meaningful detail, which means we are moving from the stage of simply knowing that planets exist to the stage where we can begin comparing their chemical environments to those of Earth and other known planetary systems. And this transition represents a major shift in the search for life, because it allows researchers to move beyond statistical estimates of habitability and begin examining actual physical and chemical conditions on distant worlds. Despite these advances, no confirmed detection of life has been made on any exoplanet so far, and even the most promising signals remain under active investigation, because the challenge is not only detecting gases or molecules, but also interpreting them correctly in the context of unknown planetary environments where non-biological processes may produce similar chemical patterns. And this is why repeated observations, independent verification, and cautious interpretation are essential parts of the scientific process. The presence of water vapor, carbon-based molecules, or even potential imbalances in atmospheric gases can be suggestive, but they are not sufficient on their own to confirm biological activity without stronger supporting evidence. Even so, the significance of the James Webb era lies in the fact that, for the first time in human history, we are beginning to reach a level of observational precision where distant atmospheres can be studied directly rather than inferred indirectly. And this means that we are approaching a threshold where future instruments or extended observations could potentially detect more convincing combinations of gases or chemical patterns that are increasingly difficult to explain without biological processes. While no one can predict exactly when or if such a discovery will happen, the current trajectory of technology suggests that we are moving closer to a point where detecting possible signs of life on distant exoplanets is no longer purely theoretical, but a realistic scientific goal within the capabilities of upcoming generations of telescopes and missions. JUD is GSZ 14-0, the latest distance holder. The most distant signals we can currently observe do not come from planets or moons within our galaxy, but from entire galaxies that existed when the universe itself was still in its earliest stages. And among these ancient structures, one of the most extreme examples is a galaxy known as JUD's GSZ 14-0, which has become famous in modern astronomy because it represents one of the farthest confirmed objects ever detected, meaning that the light we are seeing from it has travelled for more than 13 billion years before reaching our telescopes. And this immediately places it in a completely different category of observation compared to anything within the Milky Way or even nearby galaxies. Because when we observe this galaxy, we are not seeing it as it exists today, but as it was when the universe was still extremely young, shaped very differently from the cosmic structure we know now. At that time, galaxies were still forming, stars were being born at a rapid rate, and the chemical environment of space was far simpler than it is today, yet still complex enough to begin building the elements required for planets and potentially the foundations of chemistry that could one day support life. To understand why this galaxy matters, it is important to first understand what distance means in cosmic terms. Because when scientists say that JUD's GSZ 140 is more than 13 billion light-years away, they are not simply referring to physical separation in space, but to time as well, since light takes time to travel. And the light we detect today began its journey when the universe was only a small fraction of its current age, meaning we are essentially looking back in time to observe a stage of cosmic history that no longer exists in its original form. This is possible because light travels at a finite speed, and even though it moves incredibly fast, the universe is so large that light from extremely distant objects requires billions of years to reach us, turning telescopes into time machines that reveal earlier and earlier epochs of cosmic evolution as we look farther into space. One of the most important concepts needed to understand this observation is redshift, which is a phenomenon that occurs because the universe is expanding while light travels through it, causing the wavelength of light to stretch as space itself expands, shifting it toward the red end of the spectrum. And the greater the distance an object is from us, the more its light is stretched, meaning that extremely distant galaxies like Jades GSZ 140 appear heavily redshifted because their light has been traveling through expanding space for billions of years. And this redshift is not just a visual effect, but a measurable property that allows scientists to estimate how far away and how ancient these galaxies are. In simple terms, redshift acts like a cosmic stretching of light, where the original colors emitted by stars in that galaxy are shifted into longer wavelengths by the expansion of the universe during the entire journey of the light toward Earth. When we observe a galaxy like Jades GSZ 140, what we are actually detecting is not its current state, but a frozen image of its past, preserved in photons that have traveled across almost the entire history of the universe. And this makes it an essential object for understanding how early cosmic structures formed, because it provides direct evidence of what galaxies looked like when the universe was still in its infancy, only a few 100 million years after the Big Bang. At that stage, the universe was very different from today, with fewer heavy elements, rapidly forming stars, and galaxies that were smaller, more irregular, and still evolving into the structured systems we see in the modern cosmos. One of the most surprising discoveries from observing galaxies at such extreme distances is that star formation and chemical complexity began earlier than many scientists once expected, because even in these early galaxies, there is evidence that stars had already formed and lived their lives, producing heavier elements such as carbon, oxygen, and other building blocks necessary for planets and complex chemistry. And this is important because it shows that the raw ingredients for planetary systems were present much earlier in cosmic history than previously believed. These heavy elements are produced inside stars through nuclear fusion and are released into space when stars die, meaning that even early galaxies were already beginning to enrich the universe with materials needed for planet formation and potentially for life-related chemistry. However, it is very important to be precise about what this means in relation to life, because observing a distant early galaxy is not evidence that living organisms existed there, and there is no suggestion that we are seeing biological activity or alien civilizations in such ancient systems, but rather that the chemical foundations required for life as we understand it may have formed earlier in the universe's history than once thought, which expands the possible timeline for when life could begin elsewhere in the cosmos. In other words, we are not seeing life in these galaxies, but we are seeing conditions that may eventually lead to the ingredients necessary for life, such as stable elements, early star systems, and potentially planet-forming materials. This distinction is extremely important because the excitement around early galaxies can sometimes be misunderstood. But scientifically, what matters is not the presence of life itself in these observations, but the speed at which the universe transitioned from simple hydrogen and helium after the Big Bang into more chemically diverse environments capable of forming planets and complex molecules. If heavy elements formed quickly in early galaxies like Jades GSZ 140, then planetary systems may also have formed earlier than previously expected. which would expand the potential time window in which life could have begun anywhere in the universe, even in its earliest cosmic eras. The detection of such distant galaxies relies heavily on advanced instruments that can capture extremely faint infrared light, because as light travels across expanding space and becomes highly redshifted, much of it shifts into infrared wavelengths that are invisible to human eyes, but detectable by sensitive telescopes designed for this purpose, allowing astronomers to reconstruct images and spectra of galaxies that existed billions of years ago. These observations require long exposure times, careful calibration, and sophisticated data analysis to separate real signals from background noise. But when successful, they provide one of the clearest windows into the early universe available to science. Another key aspect of studying galaxies like JADAS GS 14-0 is understanding that they help map the timeline of cosmic evolution, showing how matter organized itself into structures over time, starting from simple gas clouds after the Big Bang, and gradually forming stars, galaxies, and eventually the complex cosmic web we observe today. And by analyzing galaxies at different distances, and therefore different points in time, scientists can build a layered picture of how the universe developed its current structure. This includes understanding how quickly stars formed, how rapidly heavy elements spread through galaxies, and how early environments evolved to become more chemically rich and diverse. From a life perspective, the most important implication of these observations is not that life has been found in such distant galaxies, but that the universe may have become capable of supporting the chemistry needed for life earlier than expected. Which means that if life is not extremely rare, then it could have potentially begun in multiple places throughout cosmic history, including very early epochs shortly after galaxies formed, provided that suitable planetary systems existed at those times. This idea pushes the potential origin of life in the universe closer to the cosmic dawn, although it remains entirely theoretical and not supported by direct biological evidence. If life were ever discovered in a system as distant as one associated with such early galaxies, it would fundamentally change our understanding of biology in the universe, because it would mean that life can arise under conditions much earlier in cosmic history than previously believed, suggesting that biology is not limited to late-stage chemically mature galaxies like our own, but could potentially emerge wherever the basic ingredients of chemistry and stable environments exist, even in the early universe. Such a discovery would imply that life is not only widespread in space, but also deeply connected to the earliest phases of cosmic evolution. Despite the incredible reach of modern telescopes, we are still observing these galaxies only through their light, without any direct ability to examine planets, atmospheres, or biological signatures within them, and all conclusions about habitability or chemistry must be inferred from the behavior of starlight and galaxy spectra rather than direct sampling. Meaning that while we can study the conditions of early galaxies in detail, we cannot yet connect them directly to life in any confirmed way. So what is the furthest point from Earth that still has life? At the end of everything we have explored, from Mars to frozen moons, from hidden oceans to distant exoplanets, and even to galaxies formed near the beginning of the universe, the question still returns to its simplest form. What is the furthest point from Earth that still has life? And the answer depends entirely on how strictly we define the word life, and how carefully we separate confirmed fact from strong possibility. Because in science these categories do not always overlap, and the distance of a place in space does not automatically tell us anything about whether life exists there, yet it shapes how difficult it is to know the truth. If we begin with the strictest scientific definition, where life must be directly confirmed through observation, measurement, or physical sampling that leaves no room for doubt, then the furthest point from Earth that still has life is Earth itself, because despite decades of exploration, no organism has ever been confirmed on any other world. No microbial life has been directly sampled beyond our planet, and no biological system has been verified anywhere outside Earth's biosphere, meaning that all confirmed life in the universe, based on current evidence, exists only here, from the deepest ocean ecosystems to the highest mountain microbial communities, from underground rock systems to polar ice environments, and everything we know about biology beyond Earth remains unproven and still in the stage of investigation or hypothesis. If we slightly expand the definition to include life carried by humans or machines, then the boundary extends beyond Earth into space itself. Because for more than half a century, humanity has continuously maintained living organisms in orbit aboard spacecraft and space stations, where astronauts live and work in microgravity environments far above the surface, and where microscopic life forms from Earth, such as bacteria and other resilient organisms, have been found surviving in controlled spacecraft environments or attached to equipment despite strict sterilization procedures, showing that life from Earth can persist even in the harsh conditions of near-Earth space, although this is not independent alien life, but rather an extension of Earth's biosphere into orbit and nearby space environments. If we move further outward and ask where native life in our solar system is most strongly suspected, but not yet confirmed, the focus shifts toward ocean worlds such as Europa and Enceladus, because these moons are believed to contain liquid water oceans beneath their icy surfaces, and both show evidence of chemical activity that could potentially support microbial ecosystems, especially in environments where water interacts with rock and internal heat provides energy. But despite strong scientific interest and multiple indirect indicators such as plume activity on Enceladus or subsurface ocean models for Europa, no direct confirmation of life has been achieved, meaning that these worlds remain among the most promising candidates, but still unproven in terms of actual biology. Beyond our solar system, the search becomes even more indirect, because exoplanets such as Proxima Centauri b, TRAPPIST-1 system planets, Kepler 442b, and various TOI-discovered worlds are studied through the light of their stars rather than direct observation. And while some of these planets lie within habitable zones where liquid water could exist under the right conditions, and while some show possible atmospheric components such as water vapor or carbon-based molecules, there is still no confirmed detection of life or biological activity on any exoplanet, meaning that at this stage they represent potential environments rather than verified ecosystems, and everything we know about them is derived from indirect measurements such as transits, stellar wobble, and spectroscopy of filtered starlight passing through their atmospheres. If we expand the idea further into cosmic timescales and consider not just individual planets but entire galaxies, we reach a different kind of answer based on what the early universe can tell us about the ingredients for life. Because observations of extremely distant galaxies, such as Jades GSZ 14-0, show that stars had already formed very early in cosmic history, and that heavy elements like carbon, oxygen, and other building blocks necessary for planets were already present surprisingly soon after the Big Bang, meaning that the universe reached a chemically complex state earlier than once expected. And this opens the possibility that planet formation and therefore potential habitable environments could have existed far earlier in cosmic history than previously believed, even though we have no direct evidence of life from those eras and no way of observing individual planets within those galaxies in detail. To understand how we can see such distant objects at all, it is important to understand the role of redshift, which is the stretching of light caused by the expansion of the universe while light travels across space, meaning that light emitted billions of years ago from distant galaxies is stretched into longer wavelengths by the time it reaches us, shifting it toward the infrared part of the spectrum. And this allows telescopes to detect galaxies not as they are today, but as they were in the distant past, effectively turning deep space observation into a form of time travel, where increasing distance corresponds to increasing age of the universe. And this is how we can study galaxies that existed more than 13 billion years ago, even though they are no longer in the same form or may not even exist in that state today. However, even in these extreme observations, It is crucial to be precise about what is actually known, because while we can detect galaxies and study their light, we cannot see individual planets within them. We cannot observe ecosystems, and we cannot identify biological processes directly, meaning that when we talk about the possibility of life in such distant regions, we are not referring to confirmed organisms, but to the potential for life-supporting chemistry and early planetary formation under conditions that may have existed very early in the universe's history. And this distinction is essential because scientific interpretation must remain separate from speculation, especially when dealing with distances so large that direct observation of life is currently impossible. If we bring all of this together into a single structured conclusion, we find that there are multiple layers to the answer, depending on how strictly we define life and how far we are willing to extend the concept of confirmation versus possibility. Because at the most certain level, all confirmed life exists only on Earth. At the next level, life can be carried by humans into space, in controlled environments. At the next level, there are strong but unconfirmed candidates within our solar system, such as Europa and Enceladus. Beyond that, there are distant exoplanets that may have suitable conditions, but no confirmed biological signals. And at the most extreme scale, there are early galaxies over 13 billion light-years away, where the chemical foundations for planets and possibly life may have formed surprisingly early in cosmic history, even though we cannot observe life itself in those regions. This leads to the most accurate scientific conclusion that can be made with current evidence, which is that the furthest point from Earth where life is confirmed remains Earth itself, while the furthest regions where life is strongly suspected or chemically possible extend from nearby ocean worlds in our solar system all the way to distant exoplanets and even the early universe, but without direct proof. These remain open questions rather than confirmed discoveries, and therefore the true furthest point from Earth that still has life is not something science can currently pinpoint beyond Earth with certainty, even though the universe clearly contains environments where life may already exist or may have existed under conditions very different from those on our own planet. How scientists will answer this question in the future will depend on a new generation of missions and telescopes designed to move from distant hints to direct evidence, including Europa Clipper, studying Jupiter's moon Europa in detail, Dragonfly exploring Titan's complex chemistry, Mars Sample return concepts, bringing Martian rocks to Earth for full laboratory analysis, and giant next-generation telescopes such as the Habitable Worlds Observatory that will search for atmospheric signs of life on Earth-like exoplanets using ultra-sensitive spectroscopy. Early signs of life would likely come in the form of chemical imbalance, such as methane and oxygen coexisting in ways that cannot be explained by geology alone, microscopic fossil structures preserved in ancient rock, or even possible cell-like structures found in plume ice from ocean worlds, while some scientists also cautiously discuss unusual, repeating atmospheric signals that could resemble industrial patterns, although such ideas remain highly speculative and require extraordinary verification before being considered. Somewhere beyond Earth, life may exist unseen. The furthest living thing from Earth may already be out there, and its light could be on the way right now.